So today we discuss potential energy of an electric dipole. Potential energy of an electrical dipole. Okay. So previous class we discussed when dipole placed in an electric field, what will happen? Okay. So here the previous class discussed when dipole placed an electric field, in this case, what will actually happen? This electric field is external electric field. Okay. So now same condition here. So dipole placed an uniform electric field. There is the electric field. Okay, that is the electric field E. Okay, so there is a two charges, plus Q. That is a minus Q charges. Okay. Now the separation is, say that is the separation. That is a separation. Okay. Okay. Now we say that separation is D. We say separation is D, and here we get a dipole center. This point is dipole center. Okay, so electric field at point, sorry, force at point plus Q charge, in that direction. Therefore, plus Q charge. So due to minus Q charge here in that direction. Minus Q charge. Okay. So that is a similar look like a class 10 first a moment of force. Okay, calculation. Okay, if there are two forces equal, so if I apply the Couples law, so the tau torque on this side, that is a d by 2 distance. That's also a d by 2 dipole center up to on this. The torque of plus Q charge, that is the force. That is F of plus Q charge, and that is a d by 2 displacement, and tau, there is the angle also. We say that angle is theta. Sorry, that is not actually angle. Angle side look like actually angle is a parallel to electric field. Okay, this is a parallel to electric. Okay. So that is the angle is theta, and this angle also is a theta. Okay, so that is d by 2. So we get a d by 2 sine theta, and similar tau for minus Q charge, F Q, that is similar d by 2 sine theta, and you know the couple, that is equal to tau total torque, F plus Q d by 2 sine theta, that is the F of minus Q. Okay, that is only consider charge. Okay, not only the plus or minus sign. We know that that is a d by 2 sine theta. Okay, so if I get common of F plus Q or minus Q, both charges are same. Actually, dipole have the both are the magnitude of two charges of same, but they are in opposite polarity. Okay, one is plus, another is minus. So if a plus Q and minus Q, consider the magnitude only. That is a d by 2 plus d by 2 sine theta. So F of plus Q d by 2 d by 2, if I added these two, so you get it just only d sine theta. Okay, and what is the value of FQ? That is Q times E d sine theta, that is the tau. And now we know that P dipole moment. Okay, previous class, previous among one or two class back we discussed what is a dipole moment. Okay, the vector, and dipole moment always goes from the vector minus to plus direction, minus to plus direction. P minus to plus. So here there is a torque, means this torque rotate in that direction, this torque is rotated due to that direction. So actually there is a clockwise rotation. Okay, that's very important. There is a clockwise rotation, and the P that is equal to charge, both are same magnitude, to consider one Q, and the distance is D, QD and P in vector direction. And the rotation is clockwise rotation clockwise. Okay, so finally if I get a QD sin theta, if QD means actually that is the P, so PE sin theta, that is tau. And we know that if I vector algebra, so if A cross B, we get this a both vector product, that is AB sin theta. Actually AB sin theta is also a vector. So now that is equal to, means tau is a vector, that is a P cos E. Okay. So here P cos E means if P parallel to actually E, okay, P and E if are both in parallel, let me say that if P and E, there is an angle also actually, if P in that direction and E also in that direction is parallel, so theta is equal to 0 degree. So that is tau equal to sin 0 0. Okay, that is PE sin 0 degree, sin 0 0. So total net torque be the 0. And if there is an anti-parallel, actually P anti-parallel to E, so theta is 180 degree. So tau PE sin 180 degree also be the sin 180 degree, that is also equal to 0. So actually this is look like a oscillation here, that is look like a pendulum actually. Okay, so oscillation, if I bending here, they actually look like this. If I consider that is electrically in that direction actually. Okay, if dipole place like this, if this look like a dipole place, if one is plus and another is minus, and that is dipole center and electric field oriented, that is angle theta. So here is some oscillation. So if we call clockwise rotation, so here when plus charge goes here and minus goes there, dipole actually orient like this parallel to E, so means a torque 0, so that means no rotation. That means no rotation. So just slight move, that is a mean position, that's only slightly rotation here. Similar condition, if electric field is look like this, E, and dipole now look like this, plus and that is a minus, okay, and that's the dipole center and that's the electric field E. Okay, so we know that its rotation is look like this. If the top is force in that direction plus and this force in that direction is minus. So here the rotation is now look like this. If that is this, okay, that will say anti-clockwise rotation actually. Okay, so if both are in opposite direction, okay, actually, so P minus to plus, so P actually in that direction now. Okay, here is some angle obviously. So finally, if I want to parallel to each other, okay, so either they also the balancing, now this is the balance final, and if plus goes here, minus goes here, the dipole is parallel to E. If dipole is parallel to it, means a torque 0. So no rotation, that is a to and fro motion. If you see these two diagrams, it look like an oscillation. That's to and fro motion. Okay, that's a to and fro motion. If I change the direction, obviously, if I change that, say that is a If that is a plus, here that is minus. So obviously we look like that is rotation is now electric field. Okay, so P in that direction, electric field in opposite direction. So that is anti-clockwise. If anti-clockwise means that theta equal to 180 degree, but same condition tau equal to 0. So these two diagrams, you see, analyze these two diagrams perfectly and carefully, you see that this is look like an oscillation, pendulum. Look like an oscillation or a pendulum. Okay, like this. This is the rotation, to and fro motion. So if there is an energy introduced in this, if that is an oscillation, so potential energy associated with the orientation of electric field. So if I write down some notes here, if potential energy can be associated, potential energy can be associated with the orientation of electric dipole, orientation of electric dipole in an electric field, dipole look like a pendulum. Then dipole looks like pendulum. The dipole is look like a pendulum, to and fro motion. Okay, so that is again some work done. We get some work done W, and that W that is associated with the potential energy U. Y minus sign. Okay, so if I calculate, so U means actually see that if body is at rest, okay, if body is in rest, so potential energy is maximum, and body is in motion, then potential energy is minimum. So what is the delta U? Delta U represent that is final energy minus initial energy. If initial energy is maximum and final energy is less than initial energy, so actually minimum minus maximum, we get a minus result. Okay, so that's a minus put here. That is change in energy delta U. That is related to W. So actually calculate work done by the field on the dipole when the dipole rotated in the value from theta to any 0 degree. With calculating the work done, calculating work done by the field on the dipole when dipole is rotated, when dipole is rotated to the value to suppose 0 from theta or theta from 90 degree. Okay, to theta from any 90 degree value actually. Okay, so we know that if U is potential energy of a dipole, that is equal to minus W, and that is equal to minus from 90 degree to any value theta, from 90 to any value of theta, and work done we know that is called force times displacement, but in circular motion that is tau times d theta. Okay, and you know that tau that is equal to here to get P E sin theta. Okay, tau that is where we get P E sin theta. So minus 90 degree to theta, that is a PE sin theta times d theta. Okay. Now another important thing is that the rotation is clockwise. Okay, the rotation is clockwise. Okay, so clockwise rotation means the negative torque. Clockwise rotation means a negative torque or moment of force. So that means here you get a clockwise rotation. Okay, get a clockwise rotation. Here we see that these diagrams show that is a clockwise rotation actually. So that means a clockwise rotation means minus. So here the minus, these minus means cancel out. So you get 90 degree to theta sine theta. Sorry, so that is the PE. Okay, sine theta d theta. Now P is constant. 90 degree to theta sine theta d theta, and you know that from class trigonometry. Okay, integration of sine theta, that is minus cos theta, that is 90 degree to any value of theta. So that is equal to minus PE cos theta, and these minus and that minus is plus PE cos 90 degree, and you know that cos 90 is 0, that is equal to 0 means 0, we get minus PE cos theta. Okay, so here we get final U, that is equal to minus P dot E. That is a very beautiful equation. We know that energy is a scalar quantity, dipole moment is a vector, electric field is also a vector. If there is a vector dot product, result is scalar, that's verified. Okay, verified from vector law or vector mathematics. Okay. Now in that case, now we apply some boundary condition. Okay. The boundary condition say that if P parallel to E, boundary condition applying boundary condition apply some boundary condition. So means basic boundary condition, if P is parallel to E, if P is parallel to E in same direction actually, in same direction, P and E are in the same direction. So we get U equal to PE means same direction cos 0, 1, that is equal to minus PE joule. So theta equal to 0 degree. Okay. Next case, one, number 2. If is P parallel to E, if P is anti-parallel to E, means the opposite direction, means like that E goes in that direction, P goes in the here. So that is theta equal to 180 degree. Okay. So cos 180 means a minus. So cos 180 is minus 1. So U, that is equal to plus PE joule. Here these two cases, we get some potential energy. When the dipole rotates from initial orientation like theta I to theta f, the work done on the parallel by the electric field is easy. That is U initial minus U final. Now note that. Okay. So when dipole rotates, when dipole rotates, okay, from initial orientation theta to theta f, from theta I to theta f, the work done by the electric field, that is also equal to W, that is equal to minus delta U, that is minus final minus U initial. So we get U initial minus U final. The change is orientation. Okay, if I change the orientation like that, is caused by applied torque. Actually, if I change the orientation like that, if I change the orientation, if the change the orientation, change the orientation is caused by applied torque, caused by the applied torque, important. Okay, actually commonly said that due to an external agent. Okay, actually external agent, then the work done on the dipole on the dipole by the applied torque, by the applied torque is negative. Torque is negative when the work done on the dipole of the field, work done on the dipole, by the field, that is a WA. Okay, that is also a minus W opposite. Okay, that is a final minus initial in that case actually. Clear? That is the potential energy or energy of an electric dipole. Clear? Very easy concept. Okay, that's actually if you practice 2 or 3 times, then very easy. Okay, so today end the class here. Thank you.